Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to look into using conventional probe UT and beam set in BeamTool and see how we can use these tools to get better understanding of our inspection results with conventional UT. To demonstrate these tools, we are going to look into inspection of a single V with 30-degree bevel in a flat piece. The first step is to load a probe. So we go to the probe option and we can choose conventional UT. When we choose conventional UT, first, by default, we will see a wedge and a conventional probe, which is a single element probe connected to that, and you will see the nominal refraction beat path with beam spread. We can use these. You can use these bars to move probe back and forward, and then if we click on this icon here, we get all the details we need to know about this probe and wedge. This menu divided to three sections. The first section, as we go through it shortly, shows all the information with respect to the beam that is generated. The second section gives us all the information with respect to the transducer or the conventional probe that is being used. And the last piece gives all the information, dimensional information, velocity, and all other information with respect to the wedge. We can choose what probe and wedge we want to use by choosing the manually change options here in terms of different key parameters, either in the probe or wedge, or if you want to use a specific probe and wedge that is common from a manufacturer, we can load it from the catalog. So if you go from import from a catalog, we will have a list of options of the common probes that are being used. And for this purpose, for this example, I want to use C551 from Evident. And as soon as we load that, all other information of that probe is being updated. So this will be a round probe. Its frequency is 5 and its height is 10 millimeter, which is basically the casing. And the diameter of the probe is 9.53 millimeter. To go with this, since this is a 60-degree bevel, ideal scenario would be to hit this bevel as close as possible to normal, which would be 60 degree. So I want to load a wedge that gives me close to 60 degree nominal shear. And when I click that, all information of this wedge that is selected are presented here. And now I notice that it's slightly higher than 60, 61.6, 0.6, but this is already appropriate for this bevel. So at this point, now that we have this probe and wedge, the next thing we want to know specifically is that what kind of movement, axial movement, we need to make sure that we fully cover this bevel. So in this case, what we can do is we can use the bar here that basically moves the probe left and right. And you notice that when we want to go all the way to the bottom of a root, the beam needs to be as close as, beam exit point need to be as close as 32 millimeter from the wedge center, or we can use the linear ruler here to basically see that it's around 18 millimeter from the center of the weld. And on the other end, we need to move back to cover all the way to the has, basically like somewhere like around here, which gives us around 90 millimeter from the beam exit point to the center of the weld, or close to 75 millimeter when we have the front of the wedge with respect to the center of the weld. Now when we go back to the options here, we have on the beam section, we have a bunch of options that we can take advantage of in terms of understanding that what our inspection is happening or what is going on in the inspection. The first one that I want to show you is here, the mode that we are choosing. Obviously here we created a beam, we chose a wedge that creates a shear beam. So it makes sense that the beam that we chose be shear. If the angle of the wedge was such that we could create both modes, we could also choose compression, but that will not be an option here because the angle of our wedge is past the critical, the angle of the wedge is past the critical angle for creating compression. So here, when we choose compression, beam tool show no beam because no beam gonna refract into the piece. So we go to shear beam. The next option here that I want to look at and show you guys is the beam spread. So as we know that in general, you can take and turn this on and off. So you see the beam spread because all we know is that when you have a probe, it's not like you only have one laser beam around the main angle. You always have a spread around. And parameters such as frequency, such as the diameter of the probe specifically can affect your beam spread. So for instance here, if I increase my, you can see that if I increase my frequency, my beam spread decreases. And similarly, if I lower my diameter of the probe, the beam spread gonna increase. So this will be a visualization to show how spread our beam are. The next option would be a near field representation. And here, this basically tells us what's the natural focus of the probe and where we can expect to see that. Typically, in this conventional inspection, we want to make sure that when we do the inspection, we be past our near field to have a more stable pressure field. And this is the case that for this shows that this tool shows that for this case, this is a good probe and wedge because now if I move to the point that I want to go to my second leg, always my second leg is past my near field, which is kind of what you like to do happen in this kind of inspection. Next option that I want to look into is Snell's law. So Snell's law here is a representation that show what would be the basically like an alpha angle or the angle with respect to normal inside the wedge and what's the refraction angle. These will match with our wedge angle and refract angle because as we know with the conventional probe we always shoot normal to the face of the probe, which then this angle would be equal to the angle of the wedge, and what we refract would be what nominally we want to refract from our wedge. The next reading here, which can be very useful, is what show that this display surface distance dimension. So here, for instance, you can see that what kind of difference you can get or what kind of distance you can get from your beam exit point to the surface after full V-path skip. So that is very helpful because if we essentially have a reflector, let's say a crack type of reflector on the OD, you will know that when you move back and forth, it would be basically 71 millimeter until you catch such a reflector. The next tool that can be useful is show the distance along the whole V-path. So if on the instrument we are on the V-path system to basically see what the travel path is, that's what we can easily read to make sure that the indication come from the OD or from the ID. Another tool that can be very helpful here, and for that I just want to temporarily turn off the near field and my beam spread. The other tool that can be very useful would be the crop mode. Crop mode is the choice that how we want the beam to be presented in terms of the propagation. If we choose a skip, obviously we can choose how many skips we want. In this case, we are hitting a crack or a defect, so the skips are shown after hitting a defect. But if we essentially move to locations that there are no interaction with defect, we will see that we keep having these number of skips, and here I have 1, 2, 3, 4 skips. But other than skip, the other option we can use here would be distance from the element or time from the element. So for instance, if I choose time from the element, the beam will be presented as much time, so if I start from 0, it means that the beam has not started, and if I keep increasing the time, like all the way to close to 3 microsecond, the beam reached to the wedge piece interface, and if we keep increasing, we would know that what time we have from the element. So let's say that we have a lack of fusion here on the bevel. So if now we increase our time and move the probe closer to where it's supposed to hit this lack of fusion, we can get an idea about what time along our signal will appear in our A scan. The peak for this will appear in this scan. So here, if you have 23 microsecond from the probe all the way to this lack of fusion after skip, that means that we should see an indication around 46 microsecond, which is double this path in our A scan. And if we do, that easily corresponds to the location of the lack of fusion. And you can think about this in another way, is that if we basically see an indication appearing around 46 microsecond, we can easily, by choosing the travel path from the piece and moving it back and forth, get an idea of where this signal is coming from, and then try to correlate it with the indication that we might have detected. Now, all these tools are available, but to even make it simpler to see, we have this A-scan display or simulator tool. When we click on A-scan display or simulator tool, what will happen is that now we can essentially simulate the A-scan that we will get from the beam that is there. So as explained earlier here, for instance, you see that in our A-scan, we have a peak that is coming from skipping into this lack of fusion. And if I move on to that, it kind of show you the presentation of how that A-scan peak is generated. And as you see on the screen, that's the blue highlighted path that skip and come back. Obviously, now if we move the probe back and forth, now that we don't interact with this, then we will not have any peak. But when I get here, that there is a reflection, we have a peak. Similar to that, we can also see, if we increase the time, we can also see what kind of interaction we get from our crack. And again, here you see that because now we are on the second skip and the longer travel path, specifically now the peak that we get from the crack is at the longer travel time. So all these tools that are available here can really be helpful after you design inspection team to correlate the indications in your A-scan and correlate back to where the reflection come from, and then based on where the reflection come from, you can get an idea about what type of defect you are detecting, and also that can help you with characterization. I hope you enjoyed this video, and see you in the next videos. Thank you.